In 2006, a national referendum was passed to approve the proposed expansion of the Panama Canal. The objectives are to keep this maritime route competitive and increase the capacity of the canal to accommodate larger vessels. In midsummer of 2009, the design and construction contract of this project, known as the third set of locks, was issued to Grupo Unidas por el Canal, or GUPC. The existing canal accommodates ships with a capacity of 4,400 metric tons, having dimensions of 294 meters long, 32 meters wide, and a draft of 12 meters. The third set of locks accommodates ships having a capacity of 12,000 metric tons, having dimensions of 366 meters long, 50 meters wide, with a draft of 15 meters, ushering in a Neo-Panamax class of ships. The construction of this project required excavation of 52 million cubic meters of earth and pouring 4.4 million cubic meters of concrete. Embedded in the concrete is 192,000 tons of rebar. The concrete used for this project is the equivalent of 2 Cheops pyramids for both the Atlantic and the Pacific set of locks, and the amount of steel used is the equivalent of 19 Eiffel Towers. The main objective of the hydraulic system are to minimize the use of fresh water from Gatun lakes using water savings basins as shown in this diagram. Additionally, filling and emptying times are minimized, thereby maximizing the number of transits through the set of locks. While filling and emptying, it is also vital to maintain equal Hauser hydrodynamic, hydrostatic, and slope-induced forces on ships so that they remain positioned in the center of the chamber. The main components of the canal are the water savings basins, trifurcations, filling and emptying conduits, ports, and of course the lock gates. From 2002 to 2008, the consortium post-Panamax performed several studies for ACP in order to achieve the preliminary design of the new set of locks. This included numerically modeling the trifurcations, ports, filling and emptying conduits, using a variety of computational fluid dynamic programs, or CFD. During 2007 to 2008, a 1:30 scale physical model was fabricated from the CFD studies to validate the optimized numerical model. These lock gates, operated by electric winches, take approximately 3 to 4 minutes to open or close and can operate with a differential of 10 centimeters water level. The dimensions of these lock gates are an impressive 10 meters wide and approximately 58 meters long. The height, which depends on the lock, varies from 23 to 33 meters high, and the weight of the gates also varies with the lock and ranges from 2,000 tons to just over 4,000 tons. Alden, Cameron, Flowmeter Services, and Renaissonic combine their engineering skills to devise a test program in order to test ACP's requirements for the hydraulic performance of the canal. Recognizing the complexity of testing, a custom data acquisition system was designed to log the necessary data in order to prove that the owner's requirements were met. For each side, one data acquisition system interfaced to 4 acoustic transit time flow meters, 6 each radar level sensors, 24 pressure transducers, and 80 analog inputs for plant instrumentation that sensed valve positions and other water levels. This system was used in the collection of data for the guarantee tests that were performed as part of the commissioning of the canal, and I'm happy to say that all the hydraulic performance requirements were achieved. Here we see a picture of the upper left-hand corner picture is the data acquisition system installed in the control tower and surrounded by some GUPC and APC folks. The upper right-hand picture shows the mounting arrangement of some of the pressure transducers, sensing differential pressure across a valve, and below is a very nice panoramic view of the entire lock system on the Pacific side. Most of the instrumentation was installed on the lower lock. On the upper right hand side there you see one of the level sensors sensing the level on the lower lock. Below that picture is a picture of an acoustic flow meter. It senses the flow going into the lower chamber, and to its left is a typical output screen of the data acquisition system showing level in this particular screen. Pictured here is the data acquisition system in operation collecting data for one of the many tests. After the completion of the test program, we returned in August of 2016 to present our findings and were able to witness a Neo-Panamax ship passing through the canal.
Boy, he can go pretty fast when he wants to. Oh, he's out of it. Train operator fails. Failure 1 to 2.